5 hypotheses about life on Mars. Is there life on Mars? The evidence gathered so far has been inconclusive, with proclamations and denials following one another relentlessly. So much so that the attention of planetary scientists is now shifting in other directions. Although the Apollo missions have shown that the nearest destination, the Moon, is a dry world without any form of life, other worlds in our solar system may indeed hold surprises for us in the near future. Do you remember the discovery of phosphine, which was partially disproved and is still the subject of scientific debate? Well, according to some hypotheses, Venus could host bacterial life among the clouds in its upper atmosphere. Europa and Enceladus could be teeming with life in their internal oceans of liquid water. Even the lakes of liquid hydrocarbons on Titan offer some intriguing possibilities for the search for exotic life. But in this respect, despite the recurring disappointments, Mars remains the planetary environment to which we direct our greatest expectations. A well-earned confidence? Only partly, unfortunately. But this does not prevent us from formulating hypotheses in an attempt to rationalize the problem. Let's try to see how. Certainly, this smaller and colder neighbor of ours must have had potentially suitable conditions for life in the distant past. But for now, all we have are highly questionable clues, thanks in part to a questionable exploration strategy by NASA that gives the impression of being more concerned with the financial and political aspects of missions than the scientific ones. The last time the space agency conducted experiments to identify signs of living microbes on the planet was 1976 with the Viking missions. The Curiosity rover, which arrived in 2012, has the sole purpose of discovering whether Mars was able to support microbial life in the past, while the Perseverance mission, which landed in 2021, was programmed to collect geological samples that would later be sent back to Earth. Neither mission was designed to find life on the Red Planet. In fact, after decades of automated exploration, not only can we not say for sure whether life exists on Mars, but we still have strong doubts about the actual and current presence of liquid water and other elements necessary for the emergence of life. What does this mean? It means that we have wasted a lot of time and that NASA may be thinking a lot about how to get higher and higher budgets, and a lot less about what is now the only scientific priority deeply felt by the entire global population. But let's put an end to this polemical digression, on which we would also like to hear your opinion, and try to retrace together the stages of this turbulent history that links us to the search for life on Mars. The actual exploration of the Red Planet began in 1976 with the descent of the Viking 1 and 2 probes to the Chrysoplanidia and Utopia Planidia, respectively. The probes were designed to collect and analyze soil samples for organic compounds or other traces of life. The experiments consisted of 3 main parts: analysis of soil composition, search for organic compounds, and search for metabolic activity. For the soil composition analysis, samples were heated and the gas released was analyzed to determine its composition. The search for organic compounds was based on the detection of radioactive emissions produced by soil samples exposed to a mixture of organic and radioactive chemicals. Finally, the search for metabolic activity was based on the measurement of gas production by soil samples in the presence of nutrient compounds. The results were controversial. The metabolic activity produced ambiguous results that could be explained either by the presence of life or by inorganic chemical reactions. But even today, flourishing scientists are convinced that the outcome of the analysis was instead entirely positive. The whole story of the Viking, the analysis, and the controversy that followed can be found told in the video Life on Mars, Viking Probes Found It 45 years ago. Be sure to stay tuned afterwards if you haven't seen our previous video. Another fierce controversy raged around the meteorite of Martian origin ALH 84001 found in Antarctica in 1984. In 1996, the older ones among you will no doubt remember, a team of scientists from NASA's Johnson Space Center surprisingly published a study claiming the presence of fossilized bacteria-like structures within the rock. This result was first accepted and then hotly contested by most biologists, who raised several doubts about the validity of the evidence presented and proposed alternative explanations, suggesting that the pseudo-fossils could be the result of natural chemical reactions rather than biological processes. In any case, interest in the ALH 84001 meteorite remains high, and studies of its contents continue to provide important information about the history of Mars and the possibility of life on the Red Planet. After the Viking program, interest in the Red Planet waned for several years. In 1991, there was an attempt to revive Mars exploration with the Mars Observer, but it was lost. The first success, which launched the new wave of exploration that continues to this day, was the Mars Pathfinder, a lander and rover that collected data directly from the Martian surface for 2 months in 1997. The following year also saw the launch of the Mars Global Surveyor, a satellite that observed Mars for a full 8 years, allowing us to deepen our knowledge of global cycles in the atmosphere, surface details, and history of the planet. In the last 2 decades, the number of missions has multiplied, with a continuous succession of alleged momentous discoveries, but always followed by the inevitable objections, clarifications, and then almost always retractions. Water, not water. Methane, yes, and methane, no. Traces of oxygen, no traces of oxygen. A new era of Mars exploration began in 2012, when NASA's 6-wheeled Curiosity rover landed in the Gale crater. Today, the more than 150-kilometer-wide depression is home to a large mountain composed of many layers of sediment that holds traces of ancient Mars. The primary goal of Curiosity, which is still active, is to search for signs of the planet's past habitability, such as water, organic compounds, and a source of energy, the ingredients necessary for life as we know it. Finding evidence of water was easy. Scientists already suspected that the crater once held a deep lake. And indeed, Curiosity almost immediately identified a layer of rocks that could have only formed in the presence of water. Over the years, Curiosity has also found evidence of organic molecules, the elemental chemical particles of carbon-based life forms, in the crater, and it has detected signs of ancient hydrothermal activity, where heat and chemical compounds mixed with flowing water, creating possible sources of energy. The rover also determined that methane gas in the crater rises and falls on a seasonal basis, and observed occasional spikes of this gas, confirming Earth-based observations that have defied explanation for more than a decade. Such variations on Earth would be a clear sign of the presence of beings with an active metabolism. However, none of these observations has yet been definitively linked to a biological process, and there is always the possibility that these processes, which we do not fully understand, are merely limitations of characteristic signs of life. Nevertheless, we are now reasonably certain that over 1 billion years ago, liquid water flowed on the surface, with long, branching rivers feeding lakes and seas. The atmosphere was denser than it is now, and surface temperatures must have been not too far from those we have on Earth today. Everything else is still up in the air, with a whole host of clues suggesting that it is entirely plausible that there was or is some form of life on Mars. Considering all these things, a court of law would only refrain from making a final judgment on the matter. However, while we await Mars missions that are more oriented towards the search for truth, we would venture to say that in our opinion, there are only 5 scenarios capable of adequately describing the situation. Here they are. 1. There was never life on Mars. Although the Red Planet has the same basic elements as early Earth and fairly similar environmental conditions, we must assume that the circumstances that brought life to our planet simply never occurred on Mars. All the geological and chemical processes that occur inorganically have occurred. Think of the weak presence of methane and oxygen, and still occur. But the production of simple organic molecules such as amino acids and nucleotides, which are the building blocks of life, has never been initiated on Mars. This is the most conservative position and would require that all 3 allegedly positive Viking lander tests were the result of an inorganic process or falsified by contamination. This is possible, and until very convincing evidence arrives that unquestionably points to the existence of past or present life on Mars, this is likely to remain the main hypothesis. 2. There was life on Mars, but it died out quickly. This scenario is in many ways similar to the previous one, if only for the ending. But we must say that in the beginning, 4 billion years ago, things looked very good for Mars. Our neighbor was then a world with a dense atmosphere similar to that of the early Earth, with liquid water on its surface and continents with a rich geological diversity. There were active volcanoes, a magnetic field effective in stopping cosmic rays, and ultraviolet radiation, and temperatures only slightly cooler than those on Earth today. In short, there were almost ideal conditions for life to arise. And indeed, it did. Mars cozied up to its first creatures for a few 100 million years. But then, suddenly everything changed. The cause? Well, as mentioned above, just over 3 billion years ago, Mars lost almost all of its protective magnetic field, and much of its atmosphere was ripped away by the solar wind, exposing the surface to the destructive effects of cosmic rays. Sterilization of the soil that may have nipped life in the bud. Digging into the sedimentary rocks of Mars and looking for fossilized life forms could provide the evidence needed to validate or not validate this scenario. 3. There is still life on Mars, but it is hidden deep inside. This is the most optimistic but still scientifically tenable view of the state of life on Mars. It may be that when Mars lost its atmosphere, some extremolithic organisms partially adapted to the new conditions and remained in a kind of suspended animation, waiting for better times. When the right conditions arise, perhaps underground, where liquid water can occasionally flow, that life wakes up and begins to perform its biological functions. If this is the case, then there are still organisms to be found beneath the Martian surface, perhaps in the shallow sands a few meters or even a few inches below our spacecraft. NASA's Perseverance rover has just finished collecting the first soil samples, which will be brought back to Earth by a future robotic mission to try to test this hypothetical scenario. 4. There is life on Mars, albeit hidden, but not of Martian origin. 66 million years ago, an asteroid at least 10 kilometers in diameter struck the Earth, forming the Chicxulub crater and lifting enough material to obscure our planet for decades. It was the 5th great mass extinction in the history of the Earth, but not only that. Most likely, as always in such cases, a large amount of debris was also thrown into space, and then captured by the gravitational force of other planets, such as Mars, in the same way that impacts on the Moon or Mars managed to hurl material all the way to Earth in the form of meteorites. If so, then it becomes very easy to speculate that meteorites of Earth origin could have brought life forms from our planet to Mars. And why not? After all, the planets have been exchanging materials for billions of years. 5. There is life on Mars, but our spacecraft brought it to us. Finally, the last possibility. Perhaps Mars really was a barren, lifeless planet until the dawn of the space age. Perhaps spaceborne materials that have not been 100% decontaminated or sterilized have landed on the Martian surface, bringing modern terrestrial organisms with them as stowaways. After all, this has happened before. In 1967, the Surveyor 3 lander was launched towards the Moon. Before launch, the lander's camera was accidentally contaminated with Streptococcus mitis bacteria, which survived on the Moon for a full 2.5 years before the Apollo 12 crew disassembled the camera and brought it back to Earth. It would be a real hoax if, after decades of research, we were to discover that the only life form on Mars is no more than 20 years old and is of terrestrial origin. This very real and healthy fear is why we are often so biologically cautious when exploring other planets and alien worlds. Beyond these 5 hypotheses, which can summarize all the information we have at the moment, there may be other scenarios, perhaps less likely but still possible. It is possible that life originated on Earth and seeded Mars with life. It is possible that life originated on Mars and then seeded Earth. It is also possible that life predates both Earth and Mars, and that its earliest forms colonized both planets. As always, the only way to know the truth is with more exploration and more advanced tools and techniques. The Perseverance rover, the latest arrival on the Martian sands, is not only studying and analyzing the Martian soil, but also collecting a variety of soil samples that a follow-on mission in 10 years will retrieve and bring back to Earth for laboratory analysis. If successful, we may know for sure within the next decade whether there is or ever was life on Mars. On Mars, the Vikings found new life, new revelations on the mystery that NASA does not want to solve. Between August 14th and 15th, 1965, the U.S. probe Mariner 4, after a journey of 7.5 months, flew over the red planet, passing at a minimum distance of 9,846 kilometers, and soon began to send the first images of the surface to Earth. For many scientists, however, the euphoria for the complete success of the mission soon turned into a real cold shower. They expected a planet alive, even with possible traces of vegetation, and instead, the first photos were there to describe a typical lunar landscape, arid and cratered. So goodbye Martian civilizations, goodbye to any possibility of finding life evolved in that desert almost without atmosphere. It was a real disappointment for many. Nor did things improve with the missions that followed. Mars turned out to be a very complex planet, completely different from Earth, but also very different from the Moon. All photos seem to agree on one fact: the red planet did not look like a place suitable to host higher forms of life. In fact, even if the Mariner probes had categorically excluded the existence of a Martian civilization, there was always the possibility that Mars could still host some form of microbial life. Therefore, nothing was lost. The task of clarifying this aspect would have fallen a few years later to the probes Viking 1 and 2. The Viking mission was at that time the most ambitious project undertaken by NASA after the end of the Apollo era. The twin probes Viking 1 and Viking 2, both consisting of an orbiter and a lander, left for Mars on August 20th and September 9th, 1975 respectively. After a quiet interplanetary cruise of 10 months, Viking 1 entered orbit around Mars on June 19th, 1976, and began to take a series of photographs to locate a favorable site for landing. The point was finally identified, and on July 20th, 1976, the lander separated from the orbiter and after 3 hours of descent, landed on the Martian surface at 11:53 Universal Time. The twin probe entered into orbit on August 7th, 1976, and its lander landed on the Martian surface at 22:38 Universal Time on September 3rd at a point located about 6,500 kilometers from Viking 1. Very soon, the first splendid images and a whole series of chemical and physical data of the Martian soil began to arrive on Earth. It was the first time ever that a probe sent back to Earth the appearance of a Martian landscape as it could be seen by a terrestrial explorer. But the absolute novelty of the mission was that both landers had a mechanical arm capable of taking soil samples and a small internal laboratory capable of performing some simple experiments to highlight the presence of microbial life. Viking, in fact, were not only there to take beautiful pictures, but especially to search for life. Once at NASA, they used to do so. And to this end, the landers performed 3 types of experiments. The first was the gas exchange, whereby nutrient broth was added to Martian soil samples, then trying to detect some kind of gaseous emission. Before the addition of nutrients, the samples were exposed to water vapor, and to the surprise of scientists, was detected an intense emission of oxygen with traces of nitrogen and carbon dioxide. If the samples were preheated to 145 degrees Celsius, a temperature sufficient to kill any terrestrial microbe, the emission of oxygen decreased but did not go to zero. When the nutrient broth was added, the scientists detected some gas exchange, but the situation remained somewhat confusing. The second test was the famous LR, the labeled release experiment. Also in this case, to a sample of Martian soil was added a nutrient broth. Only in this case, the broth contained radioactive carbon. The idea was that if the radioactive carbon had been metabolized by Martian microorganisms, it would have been possible to see an emission of carbon dioxide, radioactive, and therefore easily detectable. The experiment was conducted by both landers. The first used some soil exposed to sunlight and Martian weather. The second took it from under a rock, so protected from UV rays, potentially harmful to any form of life. For both Vikings, the results were clearly positive. Moreover, it was noted that if the samples were preheated, the emission of carbon dioxide ceased abruptly, as if those responsible for the emission were microbes then eliminated by heat. The third experiment was the assimilation of carbon dioxide. The Martian soil samples were exposed to an atmosphere of radioactive carbon dioxide and a strong light to simulate the light of the sun. The purpose was to see if any Martian microorganisms extracted carbon from carbon dioxide, like terrestrial photosynthesizing organisms. The experiment gave a positive result in several cases, even if the preheating of samples did not completely zero the response. In summary, from the point of view of the possibility of the presence of life, the results of the experiments seemed very promising. One experiment, the labeled release, had given a very positive result, and the other two partially positive. Yet the scientists who followed the experiments agreed in drawing the conclusion that Mars had to be a biologically dead planet. This pessimistic and strangely hasty conclusion was attributed to the fact that further analysis of the Martian soil had not found any trace of organic material. This was very strange. In fact, regardless of the fact that on Mars there is life or not, a certain amount of organic molecules should still come from space. Think that traces of organic matter are present even on the Moon, where they arrived on board meteorites. Therefore, according to NASA scientists, an unusual chemistry of strongly reactive and oxidizing soil, swept by a violent ultraviolet radiation coming from the sun, could well explain the results of the experiments without resorting to the hypothesis of life. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. An interpretation that to many scientists seemed to hide something unclear, especially to Gilbert V. Levin, the creator and manager of the labeled release experiment, who since then has always been strongly opposed to those conclusions, arguing with arguments entirely shared that his experiment had instead provided unequivocal evidence of the existence of Martian microbial life. After the end of the Viking mission, Levin and his collaborator Patricia Ann Stratt analyzed for at least a decade the data of the experiments and repeated them in the laboratory on Earth using different types of soil from the most diverse sites, such as Antarctic soil. In 1997, other discoveries about extremophilic bacteria and other new hypotheses about environmental conditions on Mars gave new impetus to their research, and Levin decided to publish for the first time his conclusions, stating several thousand tests have been made, both before and after the Viking mission, with terrestrial soils and microbial cultures, both in the laboratory and in extreme natural environments. No false positive or false negative results have ever been obtained. This strongly supports the reliability of the labeled release experiment data on Mars. In a new paper defending his thesis recently produced, Levin now tells how both Viking spacecraft, even though they landed thousands of miles apart, returned the same positive results, supported by 5 different controls, and how when the Viking molecular analysis experiment failed to detect any organic molecule, NASA concluded that the LR experiment must have found a substance that mimics the metabolism of life, but not life itself. In his J'accuse, Levin also denounced that inexplicably, despite results so controversial and therefore need of immediate confirmation or denial from 1976 to date, none of the subsequent NASA landers on Mars has been equipped with a life detection instrument similar to that of Viking. And this, together with the hastily negative judgment on the results, has always been for Levin the smoking gun, the queen proof of the fact that NASA did not want to let the world know that something up there on Mars had been found for real. The official NASA version has, in fact, never fully convinced a part of the scientific community, and many have wondered if the outcome of those analyses was not the fault of experiments too insensitive or conceptually wrong, rather than the real absence of life on Mars. Levin himself, immediately after the failure to detect organic material by the molecular analysis experiment, stated that the lack could be due to a sensitivity of the instrument not adequate to the values of the Martian environment. And he brought as evidence the fact that a similar experiment conducted on Earth in Death Valley with a copy of the same spectrometer mounted on board a Viking was not able to detect the presence of bacteria or other organic material. In the meantime, other probes arrive on Mars, and with them come other good news for Levin. In 2008, among the regolith of the northern hemisphere of Mars, the Phoenix lander finds perchlorates, which are highly toxic and flammable salts, also used for the manufacture of fireworks. Navarro Gonzalez and Christopher McKay of NASA have the idea to try an experiment. They take soil from the Atacama Desert, the driest place on Earth, with a small amount of bacteria and organic compounds. And to the soil sample, they add a small amount of perchlorates, thus simulating the composition of Martian soil. They heat up to 500 degrees and they analyze everything to an exact copy of the spectrometer that in 1976 on Mars had only found the presence of a kind of solvent. The result? No trace of organic compounds, if not some molecules of chlorohydrocarbons, just the same found on Mars, and that NASA had baptized as contamination of terrestrial nature. In practice, the Viking spectrometer had destroyed burning the perchlorate, just those organic compounds of which it had to show the existence. This hypothesis is also proved by the fact that Viking detected the presence of chlorobenzene, a flammable substance that could have been originated only by the combustion of organic material in the soil samples. And this was certainly another point in favor of the thesis of Levin and colleagues. Also in favor was the news that a review of the Viking experiments by neurobiologist Joseph D. Miller of the University of Southern California had led to some puzzling conclusions. The analysis with modern statistical techniques of an experiment conducted on Earth for more than 90 days had in fact allowed to discover, according to Miller, a periodic oscillation of carbon dioxide emission with a period of 24.66 hours, coinciding with the duration of the Martian day. And according to Miller, this is a typical circadian phenomenon, index of bacterial activity. To put an end in one way or another to this long controversy on the search for life on Mars will probably be the next scheduled missions. Certainly not the Perseverance one that is landing on the planet in the next couple of days, and is totally lacking of an equipment for biological research. Maybe we'll have to look to ExoMars, the mission designed by the European Space Agency, equipped to search for life forms and able to explore the Martian subsurface. A probe that, however, has suffered major delays in its launch schedule and will not arrive on Mars before 2023. And we want to close with the words of Levin, who was interviewed about these latest revelations. When asked why, in his opinion, NASA had avoided to equip its Mars probes with instruments suitable for the search of life, he replied, "It was an absolutely intentional choice. I think that finding microbial life on Mars could have hindered the sending of other missions because of the Planetary Protection Treaty. With the consequent loss of federal funding, I can't see any other motivation." Do you want to know more about the Planetary Protection Treaty? Click on the video. Will we be the ones contaminating the Martians?